Hi guys, here we are again. So today we are going to speak about linear differential equation. Okay, so we have done many different types of method to solve first order and first degree differential equation, and the first one was variable separable method, and then we jumped to homogeneous differentiation equation. Then we jumped also for exact and non-exact differential equations. Now we are going to see and solve a different method, that is linear differential equations. So the first thing you have to understand about linear differential equation is the concept about linear. What you mean by a linear, okay, linear equation, okay? A linear equation, as we know, it is like an equation that can be represented graphically by a line, okay? Just a linear equation. But here it is a linear differential equation. What does it mean? So we have a linear differential equation as long as, okay, when each term in a differential equation, okay, including the derivative, is linear in terms of dependent variable. Okay, so in a nutshell, what we can say, it is linear differential equation if I can write an equation in this form, okay, as dy dx plus p of x y equal to qx. Now, how to see or how to understand this? Okay, so it's a linear differential equation when the derivative is linear. Here we have a linear derivative. What we mean by linear derivative? Here we have a only, how can I say, first order differential derivative. Okay, so here I have a line. If I derive this y, that is a dependent variable, here y is dependent variable, and here the derivative of y, that is dependent variable, is linear. Okay, as well as the term of dependent variable here in the equation is also linear, is a line. As you can see here, y, if you represent y with respect to x, y with respect to x, it will be a line. It's like y is equal to x, okay? So it will be a line directly. So what we mean by this, okay? Here we have only one term derivative, and this one term derivative, okay, will be here. Dependent variable is y, so here I will get y, that is one term derivative, okay, with degree 1 also, okay? As long as we have y, that is dependent variable, derivative with respect to x, its derivative, it's only one term, okay, one time derivative of y with respect to x, okay, and here we have this same y repeated only one time with degree 1. We can say that it is a linear differential equation because the derivative is linear and the dependent variable is also linear, as we can see here. Okay, now sometimes the dependent variable, it's not like that dependent variable is always like y. Okay, now sometimes the dependent variable is x, okay, and in this case, so if the dependent variable is x, so what does it mean? It means that I will have differentiation of x with respect to y one time, okay, as well as I will have here our independent variable repeated one time with degree 1, okay, as a line of x, okay, this x only with degree 1. Then it will be multiplied by a polynomial of y, and q will be a polynomial of y. Okay, when x is our dependent variable, here p will be a polynomial of y and q a polynomial of y. But when y is the dependent variable, I will get here p, okay, p is a polynomial of x, and q a polynomial of x. So what we mean, any differential equation that can be written in this form, that the dependent variable is derived once, as well as it is appearing with the degree 1, okay, and can be reduced in this form, we can call like that as a linear differential equation, okay, or a Leibniz equation. Okay, so this y or x, it's upon the kind of equation, because it's not true that dependent variable is always y. This can be x, can be y, can be r with respect to theta. So you have just to be aware about this one. As long as to check whether this can be solved by linear differential equation, you have to see whether I can reduce in this way or in that way. How to see whether you can reduce in that way or in this way? Just check for the line, okay? dy by dx, check if it is line of y with respect to, line of y timing this polynomial of x only, and equal to this polynomial of x also. And the same you can apply for this. Now the next step is just after you reduce the equation in this form, what you have to do, this next step is just to see what is your IF. Look for your IF. We know what is integrating factor. Integrating factor, it is the term that we use to reduce our how can I say, our differential equation in a easy way, so that any step can be like easy and suitable to solve the equation, okay, just like this. So, and it is a factor, so, and here the integrating factor will be Euler raised to p raised to integration of px dx. This will work out, this integrating factor will work out when we have y as dependent variable, and this integrating factor will be Euler raised to py dy, when raised to integration of py dy, when our dependent variable is nothing more than x. Okay, here dependent variable, this is integrating factor for dependent variable x, and here this is integrating factor for dependent variable y. Okay, just look at this, px y. So this is integrating factor for dependent variable of y. Look at here, py, dependent variable will be x. So this is integration factor for this dependent variable. Now what's the next step? We know that this is a factor, it's a product. So you have to pick up the result of here, then IF is equal to Euler raised to p, Euler raised to integration of px dx, then multiply by all of this term, and do the same here. Okay, then multiply by all of this term, then you'll get this expression. Okay, now, okay, you can write, okay, the solution for this linear differential equation is y time if equal to integration of if time qx dx. This is when you take y as differential, as a dependent variable. If you take x as dependent variable, then it will be x time if. We know if will be Euler raised to integration of py dy. So if integration of y, then integration of if time qy dy plus c. Okay, let us solve this exercise first, so that we can be aware about this, the way to solve this one. Okay, so now let us solve for this exercise. Okay, we will start for solving this first exercise. Okay, now check. The first thing you have to see is this function, can we reduce this function in the form? Okay, we have just to see where is our linear, okay, our linear derivative. Okay, and to find our linear derivative, we have to see if we have dy, it's okay, then we have y linear. Okay, if we have dy and y linear, then we can reduce in this way. But if we have dx and we have if we have dx, okay, and x linear, and the x is a product of p of y, like polynomial of y only, so we can write in this way. Let us check this one. See, suppose here you have this expression. Okay, here you have this expression. What to do? How to check? See, here you have dy dx, here you have 3yx, and here you have sinus. So is that possible to transform, to make x as a dependable variable? That's the question. Is that possible to transform x in a dependable variable? Check. Here you have 1 by x. Okay, it's like 1 by x. Here you have x. It is linear. Nice. It's linear. Here x is linear. Okay. But here, is that linear? No, x cubed. Okay. So to solve this one, you have to consider a linear, like derivative is linear, okay, and the dependent variable must be also a line. What you mean by line? It must rest into 1, okay? And here you can see sine of x cannot be linear, okay? And cube and x cube cannot be linear. These are different curves. So let us see for y. dy, okay, differential is linear, nice. Now derivative of y is linear. Now see, 3y. Is there any term in y? No, no terms in y. So it means that here you have only y raised to 1. So here y is linear and dy is linear. So I can write in this form, dy upon dx plus p of x and y equal to q of x. Okay, and this is in this form actually. You see, just compare this and this form, this expression and this expression with this. So what you are going to see, it will be dy upon dx plus 3 upon x, all the terms in x away from y, okay, equal to qx. Qx is sine of x and here x cubed. Sometimes it's just in this way, you can just solve by this, it's okay. But sometimes they will give you in this way. And we are going to solve this, we have to check how to solve for this way. Okay, just in this way. Okay, now how to solve this one? Now you have this, so what you have to do here, okay, after comparing here, what you have? You have p of x, okay, p of x, because it's a dependable variable here is y. P of x is equal to 3 by x, okay, and q of x is equal to sine of x upon x cubed. Now the next step is find what is integrating factor. Integrating factor will be Euler raised to integration of p of x dx. Why p of x? Because dependent variable here is y, okay, dependent variable here is y, that's why it's p of x. So p of x dx. So now just substitute in this integration. This will be integration of 3 by x dx. So it will be Euler, then 3 out, this will be dx upon x, and this integration dx upon x, this integration here will be what? Will be Euler, okay, 3 ln of x. So if will be Euler ln of x cubed, and this will be only x cubed, okay, only x cubed. Now after you find this one, what you have to see, you have to write what is the formula. The given solution will be y, that is dependent variable, time if equal to integration of if time q of x dx. Now just substitute y time, what is if? If is x squared, x cubed, equal to if is x cubed time qx, it is sinus of x upon x cubed, so it will be sine of x upon x cubed dx. So this one will be cancelled out with this one, but you're going to see integration of sine of x dx is equal to y x cubed, here plus c, okay, just forgot to write here plus c and plus c, it's okay. Now this and this will be cancelled out. Integration of sinus is minus cosinus of x plus c, and here it will be y times x cubed, okay. It's okay. In this way it is solved, okay, nice. Let us solve now for this one, the second one, second exercise, okay. For the second one, so here we have, okay, second exercise, we have dr plus 2r cotangent of theta, cot of theta plus sine 2 theta d theta equal to 0. Okay, now see, is that possible to you to reduce? Now here we do not have x, neither y, it is r and theta. How to do? You have to do the same way. See, dr, we have a linear derivative of r. So check if whether r is only a line here, if r has exponent 1, okay? See how many r are there. It's only one r. So r with exponent r with exponent 1, okay? So here r is linear and dr is linear. So you can solve it in this way. dr upon d theta plus p of theta r is equal to q of theta, depending on theta. Okay? Yeah, the letter, it's like the numbers will change, okay? But the concept will remain the same. This is what you are doing, okay? So dr r, line, it's a linear derivative and linear dependent variable. Nice, because cot theta, cotangent of theta, it is not a line. Sine of theta is not a line, so it's impossible to solve this in form, or it's impossible to get theta as your dependable variable. Yeah, just in this way. Then we have to reduce in this way. How to reduce? So here we have theta, just divide it all by theta, theta. Okay, divide it all by theta, theta. What you're going to have? dr upon d theta plus, okay, this will be 2r and cot of theta, okay, 2r cot theta plus sine of 2 theta equal to 0. Now see, this is the term in r and this is the term in theta only, okay? So I will get dr upon d theta, okay, plus 2 cotangent of theta in bracket, then separate r, equal, okay, send this guy out there, send this out there, minus sinus 2 theta. So what does it mean? It means that this one will be our, it means that here I have p of theta is equal to 2 cotangent of theta, and q theta will be equal to minus sinus of 2 theta. Okay, now let us find what is if. If will be Euler raised to integration of, so here it is theta, it will be p theta d theta, then will be integration, okay, of this one. What is p theta? 2 cotangent theta d theta, okay? So this will be Euler, 2 can be out, then cotangent is like cos theta upon sinus theta d theta. Is this okay? Now see, here above we have cos theta and here we have sinus theta. So cos theta is differentiation of sinus theta. It means that I can write like this, if, okay, if is Euler raised to 2 integration of d sinus theta all upon sinus theta. So this is equal to Euler to ln of sinus theta. Okay, sinus theta. So these two come up, you're going to have Euler raised to ln of sinus square theta. What will it be? If will be equal to sinus square theta. This is your if. Now that you have your if, the given solution will be given in, this will be r, that is dependent variable, time if equal to if time q theta and d theta. So will be r time if, it is sinus square theta equal to if. What is if? Sinus square theta time q theta. We know that q theta, it is sinus of 2x, okay, sine of 2x, negative, just be aware about this, negative d theta Now what you have to do when you get here, yeah, easily you can see sinus square. Okay, I don't know if you remember, but cos square of x minus sinus square of x is equal to cos 2x. Okay, I will just do a kind of solution here. This is true. Okay, now if cos 2x is equal to this, so I want to find what will be our sinus square theta. So this will be 1 minus sinus square x minus sinus square x. This will be cos 2x. You see? And here, this and this will be 1 minus 2 sinus square x. And then it is cos 2x. Then just do simple simplification. This will be 1 minus cos 2x by 2 is equal to sinus square of x. Okay? So this is true. So just change by x by theta. We are going to see this. This will be, sorry, this will be 1 minus cos 2 theta, okay, by 2, and here sinus 2 theta. Here it is negative, okay. Just guys, be aware, because sometimes if you just forget the negative sign, it will be a problem for you. Okay, now here just multiply this and this and this and this. Okay, it will be your 1 by 2. You can take out 1 by 2. This will be what? This and this will be sinus of 2 theta. Okay, d theta negative. Okay, this and this will be positive. This will be plus 1 by 2 integration of sinus of 2 theta and cosinus of 2 theta d theta. See, here you have sinus of 2 theta, cos of 2 theta. You know that sinus of x times cos of x, it's equal to sinus, okay, we know, just it is equal to sinus of 2x. Okay, do the same analogy. If here it is 2 and here it is 2, so it will be 2 also here, then it will be sinus of 4x is equal to sinus of 2x cos 2x. Then you are going to get this one. Okay, yeah, and here it is, sorry, 2 and 2, just twice time. So this will be then 1 by 2. This integration, we know integration of sinus, okay, here it's negative. Integration of sinus is negative cosinus. So it will be minus cos of 2 theta, okay, by 2. Plus, okay, here you have this one. This is cos of this and this and this. So, as I said, okay, if we have, I will do this again here, sinus of 2x is equal to cos 2 cos x sin x, okay, but sinus of 4x, that will be 2 cos 2x and sinus of 2x, okay, just like this, just in a logic way. So this is almost equal to sinus of 4x, but what is missing here? Here it's missing 2. Put 2 here and take 2. So if you take 2 here, it will be 4. So you get 1 by 4. And here it is sinus of 4x. Integration of sinus of 4 theta d theta. Okay? Are we together? Don't forget, here we have r sinus square theta. And here we have this expression over here. Okay? Now, this expression, what will be this? This will be will be positive 1 upon 2. Okay, 1 upon 4. 1 upon 4. Cos 2 and 2. Cos of 2 theta plus 2 theta. Okay, plus 1. Integration of sinus. We know what is integration of sinus? It's negative. Then it will be 1 by 4 minus cos 4 theta all by 4. Okay, just in this way. Now let us just write for the solution of this exercise. Then just put together all the terms. Okay, r sine square theta will be equal to 1 by 4 cos 2 theta minus 1 by 16 cos 4 theta. So here you got r sine square theta is equal to 1 by 4 cos 2 theta. Okay, yeah, I'm just forgetting a lot of time. This is plus c, plus c, plus c, it's okay, okay? Plus c, then plus c, it's okay, no problem, just add this cc. Now, it will be minus 1 by 16, 1 by 16 cos 4 theta. Okay, just in this way. Okay, yeah. Now, it's okay. You can do some simplification also if you feel like. Yeah, it's plus c. Okay, it's plus c. So this is the solution, general solution. Okay, this is the general solution for this equation. dr plus, okay, plus 2r cotangent of theta, and plus sinus of 2 theta d theta equal to 0. This is the solution, general solution for this one. Okay, now here you can just simplify also. If you feel like you can simplify, keep on do some simplification and solve this exercise. Like r here is 1 minus cos 2 theta, because here you have also sinus square of theta, so by 2, and solve 1 by 2 cos. Here you have this one, then solve this one, but it's up on you. From here it is fine. Okay, from there it's fine, it's fine. Now let us jump for another exercise, the last one. This is the third exercise here we are going to solve. This is when we have, suppose we have 1, okay, 1 plus xy square, okay, dy plus y cube dx equal to 0. Again, how to see whether this function can be solved? The first thing is just how to see how this function can be solved by linear differential equation. The first thing is just to check whether where you find dy and y only. Okay, I have just to find linear differentiation, okay, of the dependent variable, and also linear of the dependent variable must be linear, as well as the differentiation of dependent variable must be also linear. So now let us check dy here. Here we have dy. So dy is differentiation, like it's a linear differentiation, it's fine. Now let us see for y. Here we have y. Y is with raised to 1, nice, it's linear. Now this one is not linear. This is cube, cannot be linear. And this is square, cannot be linear. Now let us see for x. dx, linear differentiation, and linear, okay, linear differentiation of dependent variable, considering x as dependent variable. And check here, x will be your dependent variable. Here x is raised to 1, and here x is raised to 1. Now we can apply differentiation, okay, differentiation for linear differentiation equation or differential equation. Now who or what will be our dependable variable? X will be our dependable variable. Why? Because derivative of x is linear, and here we have linear x. Okay, both the derivative of x is linear, and x as dependent variable is also linear. So we can apply differentiation, or like we can say that this is a linear differential equation, and this will be solved as this will be solved taking x as a dependent variable. Okay, we will solve x with respect to y, derivative of x with respect to y. So what you have to do the next time, just divide it all by you can just divide it all by dy, okay, because x here is commanding, okay, and here you can just take common x and x, okay, just like this. 1 plus x common 1, then 1 plus y square, okay, and here dy plus y and y cube dx equal to 0. Now let us solve. Now that x is a dependent variable, this one got divided all by dy, and here also by dy. What you're going to see, this and this will be cancelled out. You're going to see 1 plus x, 1 plus y square, okay, then plus, here you have this expression at all, you have this y plus y cube dx upon dy equal to 0. Now we know that this expression cannot be here, okay, this has to be in the form of like dx upon dy plus p of y, polynomial of y in a product of x, okay, of x linear equal to qy, just like this. So here we cannot have any term here, so that's why I will divide this term, this guy, for all of the expression, just to take this out of here. This will be 1 plus x, 1 plus y square, okay, divided by 1 y plus y cube, and here also the same. When you divide this one, y plus y cube, okay, y plus y cube dx and dy equal to 0. Now what's the next step? This one will be cancelled out, and this one you can solve. How? Separate this one, because here I want to take, okay, a function of y only and a function of x that is multiplying by y. How we do this one? This is 1, just separate this and this, 1 y plus y cube, okay, plus here this x, 1 plus y square, and here you can take common y and you get this one, okay, take common y, you got this one, plus dx upon dy is equal to 0, just like this. So this and this will be cancelled out. What you're going to have, dx upon dy, okay, plus 1 upon y, that's a polynomial of y only, time x, okay, and this term is a term of, if you see, this is a term of y only. This is our q, and this q must be out, must be in the other member or in the other side. This will be minus 1 y plus y cube, okay. Now we can compare dx dy plus p of y x is equal to q of y. This is q of y, this is p of y, and this is dx, this is this one, okay. Okay, then just take this, p of y will be 1 by y, and q of y will be minus 1 by y plus y cube, okay, just like this. Then what's the next step? The next step is to find what is if, okay, if. We know that if here the dependent variable is x, so it will be Euler raised to p of y dy, so it will be Euler raised to 1 by y, it's like dy upon y, okay, 1 by y, dy upon y, so, okay, yeah, so dy upon y, it will be Euler raised to ln of y, and this will be only y, okay. Now that we know what is our integrating factor is y, we can directly go for the solution of this exercise, okay. What will be the solution? Now we know that it will be dependent variable time if, dependent variable time if, integration of if time q of y, okay, time q of y dy plus c. Dependent variable is x. We know that if, we have already calculated, if will be y. Then q of y, we said that it is minus 1. Okay, minus 1 upon y plus y cube. Okay, just this one. Just substitute. It's only a matter of substitution. Okay, guys? So I will repeat this one here. Maybe you are not seeing. if, x times if is equal to integration of if, okay, q of y dy plus c. Now solve. X times if is y. Integration of y, that is if, time minus 1 upon y plus y cube. Okay? Plus y cube dy. What's the next step here? Y plus this one. So, yeah, it will be easy. Now you just have to do this is xy equal to this integration y. This will be minus out. You can put minus out. So this will be y time 1 upon. Here you can take common y. Here will be 1 plus y square. Okay? And dy. This y and this y will be cancelled out. You get xy is equal to minus this integration dy upon y plus y square. Okay? You know what is this integration? Yeah, babies, even babies know. Yes, my friend used to say. Yeah, then what will be x times y is equal to minus integration of this guy. It will be tan inverse of y plus c then. Okay? And this will be our solution. Okay? xy tan inverse, it will be x times y is equal to minus tan inverse of y plus c. Okay? Yeah. This is what we mean by that. Okay? Hope you may enjoy. So we have a lot of exercise to solve on this. Okay? So see, for the exercise or for the method that we have solved till now, you can start solving, okay, all of this exercise, applying from the very beginning, okay, the very beginning method that we did, okay. Just you can apply any method you feel like and try to solve this differentiation equation, okay. The most important thing is to know when to apply a method and how to apply this, okay. If you understand why, then the concept will become easy. Oh, then the calculus will become easy, okay. Hope it can be helpful for you. Thank you very much. See you when I see you.